that you are having a quiz on Monday on pH. Okay, you're not really having a quiz on Monday on pH and POH. You are having a practice take-home quiz. Okay, so you will take it home, you will write it. I can either, once you're done, give you an answer key, or I can mark it for you, whatever your choice is. Okay, sound good? So over the weekend, you are going to do in the white book, pages 80 to 84 and 88 to 89. Obviously, you don't need to do every question, just do as much as you need to feel good about it. Yes, because some of them can get pretty tedious. If you're like, I know how to find pH from hydrogen, you don't need to spend a lot of time doing that. Yes? All right. But you're going to pretend you have a real quiz on Monday because you're going to get a take-home quiz. Unit 5, pages 6 and 7 is stuff on indicators. Page 32, 1 through 4 is finding a KB from the KA, but those are like super, super small. Do the free response question that I gave you. Give yourself 23 minutes. Okay? Just be like 23 minutes. I'm going to get done as much as I can do. And then you're going to like set that aside. If you want to write anything after that 23 minutes, you can do it on a separate sheet of paper maybe. Yes? And be like, okay, now I'm doing the rest of it, right? After the 23 minutes to see if I know it, but I just couldn't get it out in time. Okay? Then you're going to score yourself. Score what you would have gotten in the 23 minutes, and then you can score what you would have gotten outside of that time limit. Okay? Finally, you're going to read through the student performance Q&A because those are really, really powerful. What those are is it is the chief readers report. What happens is they get all the markers to give feedback about what students didn't know, what they did poorly, what some common errors and omissions were. It's a really powerful learning tool. So if you can read through that as well, that would be great. It's going to give you an idea of what a long response question looks like. I'm going to start giving you them more regularly starting next week, okay? And you're going to work through as much of the acid-base part one review as you can, given that you have all those other things to do. None of those other things are particularly long. Yes? So that's, but I know there's 2 number 2s, but apparently I can't do, you know, counting. You guys can figure it out? Yes? You can be like 1, 2, 2, 3, that's okay? Yeah? All right, good. So on to, we finished 5.2. Look, we're on 5.3 now. Excellent. 5.3 is about hydrolysis. Hydrolysis, except for we say hydrolysis, it's different than the hydrolysis in biology. Okay, so if you've learned hydrolysis in biology, this is different hydrolysis. This is on page 33. Hydrolysis is a really powerful concept, and you actually know a lot about it already. We just haven't given it a name. You guys good? No worries. Just want to make sure I'm not like zooming ahead when you're not ready. Okay, hydrolysis is the reaction of an ion with water to produce an acidic or basic solution. Have we done such things already? Yes, we have. You remember when we were doing the KBs, you put your ion and you put it with water and you end up with hydroxide, right? So, but only some ions can undergo hydrolysis, not all of them. And in fact, we've done this already. Can you guys tell me some ions that cannot react with water? Tell your partner. Maybe take a look at your data booklet. What are some ions that cannot react with water to form an acidic or basic solution? Does anyone feel brave enough to give me an ion that does not react with water? That will not react with water? Casey. HSO4 minus. You're so close. Okay? You actually just picked the wrong one. You want to give me a different one? NO3 minus. That's a good one. Okay? You know what? It doesn't react as a base, but the problem with that one is that it has a hydrogen, so it actually can react with water as an acid. Okay, so you had the misfortune of picking the wrong one. All the rest of them will work. Yeah, none of these ions here can accept hydrogen from water, yes? So if you have those ions, you will not get a reaction with water, you will not get hydrolysis, it will not produce an acidic or basic solution. So the solution will be, if it's not acidic or basic, it will be neutral. So if I had sodium iodide, that will be a neutral solution. If I have sodium chloride, that is a neutral solution. Sodium nitrate, that's a neutral solution. Potassium chlorate, that is a neutral solution. All right? So that's dealing with our anions. All the rest of the anions can react with water, yes? And we just did that last day when we were looking at how they react as bases, yes? Okay. So, yes. HS minus, we're just going to ignore that because it makes me unhappy, okay? Yeah. I've never been happy with it on the table. It kind of falls off the end, and I don't know whether it, yeah, anyway, so we'll just leave that one alone, okay? Yeah, so what you have to do is you have to take a salt, and when you're given a salt, you have to then dissociate it, because when you were doing hydrolysis, we're not just going to give you the ion, we're going to give you the salt, which contains 2 ions, yes? So let's say we have sodium chloride. We are going to first dissociate it, number 1, dissociate it, Na plus and Cl minus. Do the ions hydrolyze? In other words, what do they do? Do they what? React with water. So they either have to be able to accept a proton, or they have to be able to donate a proton, or otherwise they will do neither. They will have no hydrolysis. If they accept a proton, what that means is that water will then become OH minus, right? Because it's donating a proton to whatever it is, okay? So if this thing accepts a proton, then we produce a basic solution because we have produced hydroxide. Does that make sense? If, on the other hand, our substance gives a proton to water, what will we end up with? Water will turn into hydronium, H3O plus, and that's what's happening here. And that's acidic hydrolysis because, of course, we've made H3O plus, and so we have made an acidic solution. If we're not accepting or donating protons, then there is no hydronium or hydroxide in excess, and so there will be no hydrolysis, no neutral solution. So we actually have to look at both ions, the cation and the anion. And so we're going to look at sodium, and we're going to say, if I put sodium positive, and this is different than sodium metal, which we will review in just a moment, but if we have sodium positive with water, what happens? Can it accept a proton? Right? If it did, if we had a hydrogen going on to there, it would be NaH2+. Does that look good, or does that look Ick. Ick. Like, what the hell? Huh? Interrobang. Okay? No. And also, it does not have a proton. So can it donate a proton? No. So sodium cannot accept a proton. It cannot donate a proton, so it does not hydrolyze. In fact, no metal ions ever hydrolyze except for 3. Fe 3+, Al 3+, and chromium 3+, and they do something special when they are in water that we'll talk about a little bit later. But if you want to remember those 3, I always say remember feel creepy, because they're unusual, so they feel creepy. Anyway, I don't know, it helps me remember it, you know, anything, however stupid it is, it will help you remember it. Although actually, if you take a look at your data booklet, you don't need to memorize them. And AP won't expect you to have them memorized either, okay? So if they want you to deal with it, they'll have to give you the formula. Can you find iron, aluminum, and chromium on this chart? Go looking. Go search for iron, aluminum, and chromium. Hexaquo. Hexaquo. So what happens with these 3 is that they associate themselves with water. Okay, so in solution, and we will talk more about this, I've got some pictures later on in the book, they associate themselves with water. So although iron itself does not have hydrogens, the water that it is associated with does have hydrogens, and one of those waters, say for example, can give up a hydrogen to donate to like water in solution. Okay? Don't worry about it too much yet. You've just seen it, and we'll come back to it later. Okay? I feel weird because like everybody's over here except for you, so I keep forgetting to look over here. So I'm trying to, you know, remember you guys. Hello. Okay. So, continue. Do the ions hydrolyze? We dealt with sodium already. No hydrolysis. Does chloride hydrolyze? Can it accept a proton? Can it donate a proton? Will it do neither? Can it accept a proton? Cl. Can Cl accept a proton? Did I hear a no, 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 no? You cannot make a strong acid. It's, you take H2, neutral, and you combine it with Cl2, neutral, and you do a synthesis reaction, and you end up with molecular HCl gas. Yeah? So it cannot donate a proton, it has no proton. Can it accept a proton? No, it can't. Okay, because this is a strong acid, so we cannot do that. Apparently I was also feeling colorful today, and that, my friends, is a one-way arrow, which means Cl- cannot accept a proton. I feel better though, because every once in a while I read Hebden, and Hebden writes something like that, or Kolger writes something like that, and I'm like, oh, it's not just me. Okay, none of the conjugate bases of strong acids can hydrolyze. So we have sodium, which cannot donate and cannot accept a proton. We have chloride, which cannot accept and cannot donate a proton. So we're not making OH, we're not making hydronium, which means the solution will be neutral. Yes? So to find the pH of any salt, you need to look at both the cation and the anion. Cationic hydrolysis is very rare, okay? So you're not going to have to worry about it too much. As I said before, no metals, metal ions, hydrolyze, except who? FeAlCr, Feal creepy, okay? And there is one other that hydrolyzes, and you just need to remember it, but it's kind of memorable because it's our only positive polyatomic ion that's not hydronium. So it is ammonium, okay? So those are the 4 cations that hydrolyze, otherwise cations do not hydrolyze, okay? There are some others, but they're weird and you're not expected to know them. There'd be things like N2H5+. Yes, but you're not expected to know those. So we'll just pretend they don't exist. So another way to remember them, you can just look in the acid column and be like, oh, look, here we go. Here we go. Here we go. And you don't even have to be able to remember how to write the formula because it's given there for you. Yes? And there's our ammonium ion. So you can actually look for the ions. Notice it says ion, 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 ion. And you might say, oh, but hey, there's some other ions. But all those other ions are not cations, they are anions. So those are the only 4 there that are cations, okay? So what happens to these weird little metal ions when they get into water? They attach themselves to 6 water molecules. So you have Fe3 plus aqueous. This is hydrated Fe3 plus. What happens is that iron 3 plus has some empty d orbitals. Yes? Empty d orbitals. You don't need to know this. This is not part of the curriculum, okay? But we've got some empty d orbitals floating around. Whoops, I should have done it like that. La la la, empty d, empty d. And water comes along and says, oh, I have a lone pair that would love to slot in there because then it will be close to a 3 plus charge. Yes? Okay, and so you end up with, it's called a dative covalent bond. You don't need to know that, so I don't even know why I mentioned it. Anyway, that's how it happens. You don't need to know much about it. Here's a lovely little picture, just kind of showing you 3 different representations. Those lone pairs on the oxygen are pulled towards that 3 plus at the middle. I don't know why other ones don't. Or maybe we just don't, they're just not on our chart. That's possible too. Yes. Because it's the oxygen that's attached. So I think that's what they're showing. They're just showing it in a little bit more structural way. Okay? I don't know. Doesn't matter. It's not the H that attaches. I think that's the key thing. So if we look how these things donate, we have our hydrogen in the water, and it gets donated to the liquid water floating around, solvent, and that gives us H3O plus, and since one water gave away its hydrogen, instead of having 6 waters, now we only have 5 waters, and one of them has turned into hydroxide. The charge has gone from being 3 plus to being 2 plus because it lost a proton. Is good? Okay. So when Fe3 plus hydrolyzes, it produces H3O plus, which means the solution will be what? Acidic or basic? Acidic. Our other cation that hydrolyzes is the ammonium ion. And of course, we know what that does. It gives its proton to water. And we end up with H3O plus and NH3. And so that's going to be an acidic solution. Cationic hydrolysis always produces acidic solutions, okay? Because there's only those 4 and they're all donating protons. Yes? Anions. Do they all produce basic solutions? Well, no, because we have, unfortunately, many, what? Starts with an A. Amphiprotic anions, right? So they can act as an acid or they can act as a base. If you don't have a hydrogen, anionic hydrolysis will be basic. It will produce hydroxide, right? So if we look at potassium fluoride, first of all, we need to separate our ions so we know who we're looking at. Then we ask, does the cation hydrolyze? And we say, no, it's not ammonium. It's not feel creepy, so it does not. Does F minus hydrolyze? If you put F with water and say, will it accept a proton? We end up with HF. Is that okay? Will that occur? Is HF strong or is it weak? It is weak. And I don't think you need to have this memorized for the AP exam, but just in case, do you remember the strong acid mnemonics? Chloe Kleiberson. So I brought no clean clothes. And none of those has an F in it. So you know that hydrofluoric acid is a weak acid. Okay. So we can get that equilibrium set up so hydrolysis does occur. What was produced? OH minus. And if OH minus is produced, then the solution is basic. Okay? Easy enough? Actually, I want to bring something to your attention. I probably have it later on. But so often students will look at this and they'll be like, oh, look, I produced an acid, therefore the solution must be acidic. But any weak acid-base equilibrium will have an acid and a base in it. We haven't gotten rid of all the fluoride. We only used up some of it, right? We have this, we have this. What do we have excess of in terms of hydrogen or hydroxide? We have excess hydroxide. Yes? So never look and say, did I produce an acid or a base? Look and say, did I produce hydronium or hydroxide? That's going to tell you whether it's acidic or basic. Okay? It's just because you produced some and you didn't produce any hydronium, so you have more hydroxide than hydronium. Or yeah, if you produce one, you don't produce the other, then you must have more of it. Excess is not the right word. I should say a greater concentration. That would be a better way to say it. If the cation does not hydrolyze, just focus on the anion. If the conjugate acid is weak, we get hydrolysis, it will be basic. If the conjugate acid is strong, anionic hydrolysis does not occur and it will be neutral. Okay? NaCN. Why don't you cover up the answer and see what you can do with that? Does Na hydrolyze? No. Does Cn hydrolyze? You would want to look at its conjugate acid. Who is its conjugate acid? HCN. Is that a strong acid? No. Therefore, does Cn minus hydrolyze? Yes. And if Cn minus hydrolyzes, reacts with water, what does it produce? It produces OH. We end up with HCN plus OH minus. And so what kind of a solution have we got? Basic. You can automatically say it has to accept the proton. Yep. CaBr2. Tell me what happens with CaBr2. We have Ca2 plus, and we have Br minus. Does Ca2 plus hydrolyze? No, that one's really easy. It's not feel creepy, and it's not ammonium. How about Br minus? No, because its conjugate is HBr. So I brought no clean clothes, Chloe Kleiber, son. Okay, so no. So what's the pH? Neutral, 7. Easy enough? SrNO2 SR2 plus? No. NO2 minus? Who's our acid? HNO2. What? HNO2, okay. Now, is that a strong acid or a weak acid? It's weak. It's HNO3 that is the strong one. That's why I put this one in here, is just to remind you. Okay, we're just going to leave it there. We're not going to give you anything on hydrolysis over the weekend. You have enough to do, I believe. Okay. Alrighty. How are we feeling about hydrolysis? Good? Thank you so much. You're wonderful.